Hello everyone, welcome back to video lesson 3 of Unit 2. In this lesson, we will study about the principles of mathematical induction, which is a proof technique used to show that a given mathematical statement is true for every natural number. Now let's begin. Like I said, principles of mathematical induction is a method of proving that a mathematical statement is true for all natural numbers. So it is a method that used to show that a given mathematical statement is true for each and every natural number. Given a mathematical statement P of n, the first step is we show the statement is true for n is equals to 1 or n is equals to 2. Just depending on the statement, we start from 1 or from 2. It depends on the given statement. So once we show it is true for n is equals to 1 in the first step. Second, we assume P of k is true for some natural number k. Based on this assumption, we prove that the statement is also true for k plus 1. So inductively, the mathematical statement is true for all natural numbers. Because in the first step, we show that it is true for n is equals to 1. So if it is true for k is equals to 1, the second step, it will be true for what? K plus 1. That means when k is 1, it will be true for what? 1 plus 1. The statement will be what? True for k is equals to 2. Now if it is true for k is equals to 2, it will be true for what? K plus 1, which is 3. So if it is true again for 3, it will be true for what? 4. Inductively, the given mathematical statement will be true for all natural numbers. Now let's take a good example. Principles of mathematical induction is like a row of standing dominoes. Once you knock the first domino, it will knock the next domino. At the end, all the dominoes will what? Fall. So similar to this, if you show the given statement is true for k is equals to 1, it will be true for what? K is equals to 2. If it is true for k is equals to 2, it will be true for what? K plus 1. That means it will be true for what? K is equals to 3. So inductively, the given statement will be true for all natural numbers. Now let's take example so that you understand the principles of mathematical induction. Now show that 1 plus 3 plus 5 plus up to n minus 1 is equal to what? N square for any natural number n. Now this mathematical statement says what? The sum of the first n odd natural numbers will be equal to n square. The sum of the first n odd natural numbers will be equal to what? N square. That means when n is 1, the first odd natural number is what? 1. So 1 is equal to 1 square. When n is 2, the sum of the first two odd natural numbers, 1 plus 3, which is 4. So 2 square, it will be 4. When n is 3, that means the sum of the first three odd natural numbers, 1 plus 3 plus 5, which is what? 9. It will be equal to what? 3 square, which is 9. So in general, this mathematical statement says what? The sum of the first n odd natural numbers equals to n square. To prove this statement is true for all natural numbers, we follow the steps of the principles of mathematical induction. Now, in the first step, we are going to show the statement is true for n is equals to 1. We are going to show P of 1 is true. The statement is true when n is equals to 1. So when n is equals to 1, what will happen? On the left side, twice of 1 minus 1, which is 1, is equals to, on the right side, 1 square. So 1 is equals to 1. It is what? True. That means the given statement P of n is true for n is equals to 1. Now, second step, assuming the given statement is true for k, we are going to prove it is true also for what? K plus 1. Assume that it is true for what? N is equals to k, where k is greater than 1. Already we show it is true for k is equals to 1. So in the second step, we assume it is true for n is equals to k, arbitrary natural number k greater than 1. Now, based on this assumption, we are going to show the statement is true for k plus 1. So, assuming it is true for k means 1 plus 3 plus 5 up to what? Twice of k minus 1 is equal to what? K squared. Remember, we are assuming the sum of the first k odd natural numbers is equal to k squared. Based on this assumption, we are going to show that the statement is true for what? K plus 1. So, in the third step, we shall show that it is true also for what? N is equal to k plus 1. This is our claim. We are claiming the statement is true for n is equal to k plus 1. That means the sum of the first k plus 1 odd natural numbers is equal to k plus 1 square. Now, 1 plus 3 plus 5 up to 2k minus 1, based on our assumption in the second step, the sum of the first k odd natural numbers is equal to what? K square. So we replace the sum of the first k odd natural numbers by what? K square. This is our assumption. And we are going to prove the statement is true for what? N is equals to k plus 1. So when n is k plus 1, twice of k plus 1 minus 1, twice of k plus 1 minus 1, which is what? 2k plus 1. So we get what? Up to k, you have k squared. Up to k plus 1, we have what? K squared plus 2k plus 1. This is quadratic. K squared plus 2k plus 1. We can factorize this quadratic as what? K plus 1 square. Meaning, the given statement is also true for what? N is equals to k plus 1. Based on the assumption, the given statement is true for k, we showed that, or we proved that it is also true for what? K plus 1. Because the sum of the first k plus 1 odd natural numbers is equal to what? K plus 1 square. So the concept behind is what? Already we proved it is true for what? N is equals to 1. So if it is true for k is equals to 1, based on the second step, it will be true for what? 1 plus 1, which is 2. The statement will be true for k is equals to 2. If it is true for k is equals to 2, it will be true for what? K is equals to 3. If it is true for k is equals to 3, it will be true for what? K is equals to 4. So inductively, the given statement is true for all natural numbers. Yes, I hope you have the idea of the principles of mathematical induction. Yes, it is similar to the dominoes fall. Once you knock the first domino, then the second will fall. If the second fall, it will knock what? The third domino. At the end, all the dominoes will fall. Just similar to that, if you show it is true for k is equals to 1, it will be true for what? K is equals to 1 plus 1, which is 2. If it is true for k is equals to 2, it will be true for k is equals to 3. If it is true for k is equals to 3, it will be true for k is equals to 4. So inductively, the given statement is true for every natural number. Now let's take second example so that you understand the principles of mathematical induction. Now in the second example, the statement we have is what? 1 plus 2 plus 3 up to n. The sum of the first n natural numbers is equals to n times n plus 1 over 2. Now first you need to understand what the statement says. So when n is 1, 1 times 1 plus 1, 1 times 2 over 2, which is what? 1. 1 is equals to 1. This statement is true for n is equals to 1. When n is 2, the sum of 1 and 2, which is what? 3. So when n is 2, 2 times 2 plus 1, 2 times 3 over 2, which is what? 3. So it is true for what? N is equals to 2. When n is 3, the sum of the first 3 natural numbers, which is 3 times 3 plus 1, 4. 3 times 4 over 2, which is what? 6. 1 plus 2 plus 3, that is also what? 6. So based on the principles of mathematical induction, we are going to prove this mathematical statement is true for every natural number. And now let's start. Now the first step, as usual, we are going to show the statement is true for n is equals to 1. That means the first natural number, that is 1. 1 on the left side is equals to 1 times 1 plus 1, which is what? 2 over 2. Again 1. So 1 is equals to 1, it is true. That means the statement is true for k is equals to 1. Second step, assuming the statement is true for k greater than 1, we are going to prove it is also true for k plus 1. Assume that it is true for n is equals to k means the sum of the first k natural numbers is equals to k times k plus 1 over 2. This is our assumption. Now based on this assumption, we are going to show the statement is true also for k plus 1. We shall show that it is true also for k plus 1. So if we prove it is true for k plus 1 also, then inductively the given statement is true for every natural number. So in the third step, we are claiming the sum of the first k plus 1 natural numbers is equals to k plus 1 times k plus 1 plus 1 over 2. So in the second step, we assume that the sum of the first k natural numbers is equals to what? K times k plus 1 over 2. So the sum of the first k natural numbers is equals to what? K times k plus 1 over 2. This is our assumption. And based on this assumption, we are going to show that the sum of the first k plus 1 also equals to k plus 1 times k plus 1 plus 1 over 2. So the sum of the first k natural numbers, k times k plus 1 over 2 plus k plus 1. We are going to simplify this expression to get k plus 1 times k plus 2 over 2. So the sum of these two means 2 times k plus 1 plus k times k plus 1 over 2. Again, k squared, k plus 2k, that is what? 3k. And the constant term, that is 2. So k squared plus 3k plus 2, this quadratic expression is the product of k plus 1 and k plus 2. K squared plus 3k plus 2. When you factorize this quadratic expression, you will get k plus 1 times k plus 2 over 2. So we prove that the statement is also true for k plus 1. The sum of the first k plus 1 natural numbers is equals to k plus 1 times k plus 2 over 2. So inductively, the statement is true for every natural number. I hope you have the basic concept of principles of mathematical induction, and don't forget to practice on similar statements. Practice again and again, because as you know, mathematics is learned through practice. So with this, we come to the end of lesson 3 of unit 2. If you don't subscribe my YouTube channel so far, please subscribe and turn on the notification bell. Thank you. See you in the coming lesson.